Namaste and a very good evening to all of you. I welcome you to my channel, The Outlier. My name is Matul. In today's video, I'll be talking about the basics of deep learning using what is called as the TensorFlow playground. Even before I get started with the basics of deep learning, may I request you to subscribe to my channel, also like and share my videos. Firstly, folks behind TensorFlow at Google have created a nice little website which is called as playground.tensorflow.org. I repeat, it's called as playground.tensorflow.org. Now, let's experiment by creating our own neural network. What is the benefit of creating our own neural network? The idea behind creating our own neural network would be that we can get a hands-on intuitive feel or of how a neural network works. I would really encourage you to head over to this particular website, which is called as playground.tensorflow.org, and experiment for yourself and see how a neural network works. You don't have to write one single line of code here, and intuitively you can understand the internals of a neural network algorithm. Our objective is to classify a bunch of points based on their location in the 2D image. You can see here, this is the image that I'm talking about. We have a few data points which are in the lower left corner, and we have a few other data points in the upper right corner. We want to create a neural network that can classify a bunch of data points as either orange or as blue, depending upon the location of these data points in the 2D image. It's pretty clear that the ones in the lower left represent one set of points, and the one at the upper left represent the second set. So this is essentially a binary class problem. I repeat, this is essentially a binary class problem. The goal, as I said, is to create a neural network that given it has no prior knowledge, can it figure out if a given point should be blue or orange? Or in other words, can a neural network predict successfully which class the data points should belong to? This is the main goal behind this particular experiment. Excuse me. Now, to begin with, let's start with a simple data. As you can see here to the left side, I have picked up a data set. This is a very simple Gaussian data set. We can use this to classify and create a neural network that is able to identify which set of points belong to the orange class and which set of data points belong to the blue class. Now, you may ask me, what are the input features? You can see here, this is the data. There are 4 different problems. We can explore each of these 4 problems one by one. These are the input features. We are going to extract x1 and x2. What is x1 and what is x2? If you look at any random data point here, it has the horizontal axis as well as it has the vertical axis. Now, if you look at this particular point here, it has a horizontal axis value of around minus 2.8 and its vertical axis value is around minus 4. So x1 represents the horizontal position of a point and x2 represents the vertical position of a point. So we are going to use x1 and x2. x1 represents the horizontal position and x2 represents the vertical position. Using the horizontal and the vertical position of a point, can we train a neural network to classify a bunch of points as orange or as blue? Now, as I already told you, we have to remember that this is a binary class problem. We either need to classify a data point into blue or orange. Now, what do you see here? This is the input layer here. We have x1 and x2. In case we want to add additional variables, we can also take the square of the first coordinate. We can also take the square of the second coordinate. We can also take the product of these 2 variables. For a more complicated pattern, maybe we need to do some feature engineering and we can take these additional variables as well. We can take sine of x1 or sine of x2 as well if need be. Now, as you can see here, this is a deep neural network. Why do I say that this is a deep neural network? Because we have got 2 hidden layers. The first hidden layer here has 4 neurons. Each of these boxes that you see are the neurons. Similarly, in the second hidden layer, you have 2 boxes. In the input, we are taking two features. And in the first hidden layer, we have 4 neurons. And the second one, we have 2 neurons. Now, the end goal, as I've already said, is to create a neural network that can reliably classify a data point as blue or orange. Let's look at the proportion of the data set that we are taking in the training. You can see here it says ratio of training to test. Currently, 50% is assigned to training and 50% is assigned to test. I might want to change this. So all that I'm going to do is move the threshold bar to the right side. I'm going to use 80% to train the neural network model. The balance 20% I'm going to use to test. You can see the existing loss function here. And at the top, you can also see very, very interesting features of a neural network like epoch, which basically represents the number of iterations. We also have another interesting parameter, which is called as learning rate. What is this learning rate? It's just nothing but the step size in the gradient descent we are doing. Nextly, we can play around with the activation function, regularization. We can also choose the regularization rate, and we are going to use a classification problem. What we are doing is typically in machine learning lingo is called as classification problem. Please keep your eye on this particular diagram while I hit this start button. The moment I hit this start button, you can see here there are the epochs, which basically means the number of iterations that the neural network goes through to learn this pattern. It has created a nice little line here, which is able to clearly classify the orange points from the blue points. I don't need so many epochs, so let me just go ahead and hit the pause button. You can see here, I know that this is a very, very simple problem. We have not done anything magnificent here. We have just created a linear separator, which is able to clearly separate the two classes. Look at the accuracy here. The training loss is 0. The test loss is also 0. Considering the fact that we have a very, very simple problem, this is expected. Now, what has happened here? You can see a lot of connections from the input to the hidden layer. Thicker the line, you can see here, there are different lines here. Thicker the line, more is the weightage. Thinner the line, lesser is the weightage. Let's focus our attention on this particular neuron. What is this neuron telling me? This neuron is basically saying, boss, I want to weight a little bit heavily on the top right-hand side. And things on the lower left corner, I'm going to give lower weightage. So you can see here, it is giving higher weightage to the points on the top right and slightly lesser weightage. In fact, I can't say slightly lesser weightage. In fact, it has given almost equal weightage to the top left as well as the bottom, sorry, the top right as well as the bottom left. Let's look at this. More or less is the same thing. Here again, each of these neurons are not doing anything extra. They're given more weightage to the ones at the top right and considerably lesser weightage, I would say, or almost the same weightage to the left side. Since it's not learning anything new, the question is, should we at all have these extra neurons? Let me go ahead and remove some of these neurons because it's not adding any value as such. Now let me go ahead and build this network again. You can see here it's able to converge again. I don't see too much of a difference between this. This is fine, this is fine, but this I would say is redundant. So instead of having a deep neural network with 2 different hidden layers, can we remove this hidden layer? The moment I want to remove this hidden layer and I just want to create a simple MLP, since it has one input layer, one hidden layer, and a simple output, I can go ahead and call this as a MLP or a multi-layer perceptron. This is what we call as a shallow network. This is the opposite of a deep network. A deep network has multiple hidden layers, but since this has only one hidden layer, I can call this as a shallow network. I'm not even comfortable with this, so let me just knock off this particular neuron. So it's very interesting. We have 2 features here, the x coordinate, the horizontal axis and the vertical axis, and we're just going to use one neuron to predict which class this set of data points and this set of data points belong to. Let me run this. Not bad. It is still able to do the job. Now, since this is a pretty straightforward problem, we could sort of classify with almost 100% accuracy. The loss is almost zero, which means basically the accuracy that we've achieved in this problem is almost 100%. We are able to achieve such a high level of accuracy with just one particular neuron. Let's just go ahead and try to do something more complicated. This is a circle problem. You can see here, the data here is a circle. And we have a lot of data points in the center. The stuff in the center are the blue ones, and the stuff outside are the orange dots. This is slightly more complicated than the earlier data set, wherein the neural network had to just draw one single line to learn the pattern. I'm sure that if I run a neural network model with just one hidden layer and one neuron, it is going to struggle. But nevertheless, let me just go ahead and try my luck. You can see here it is trying, but it is really, really struggling here, and we are not achieving much. It's got stuck. So let me just go ahead and help by giving it more neurons. Let me just click on the plus sign. Let me help this particular neural network by giving more neurons. So right now I have got 4 neurons. Not bad. Very quickly, you can see here, it has converged on the optimal solution. Not bad. A neural network in 536 epochs or iterations has been able to learn the circular pattern. It has been able to separate that and say that the data points on the outside are one class and the data point on the inside, namely the blue ones, are the second class. Look at the training loss and the test loss. They are very, very close to each other, which means that we don't have much of a overfitting problem. Now, what is happening here? Now, this is a very interesting neuron. What this has done is it has given higher weightage to the region at the top, and it has given lower weightage to the region at the bottom. Now, this neuron here is saying that I'm going to give high weightage to the ones in the left-hand side and lower weightage to the ones at the top right-hand side. Now, the third neuron here is giving even more higher weightage to the lower left-hand side region and lesser weightage to the ones at the top right. The one at the fourth neuron here is giving a lot of weightage to the bottom right, and it is giving little weightage here. You can see here there is a thick orange line, and if I hover the mouse here, it says weight of minus 3.4. As I said, thicker the line, higher the weightage. Now, the blue line here is positive 2.1. Now, this has lesser weightage. This further has lesser weightage. So using a typical MLP, we've been able to train our neural network. And once we are able to train our neural network, it is able to sort of adjust the weights. By adjusting the weights, we are able to create a model which is able to recognize and say that the stuff in the middle are basically the blue dots, and the ones at the orange, the ones at the outside are orange. I'll head over to the next data set here. You can see here, this is a slightly more complicated data set wherein I've got a lot of orange data points at the top left as well as the bottom right corner. In the right-hand side top corner, I have a lot of blue dots as well as a lot of blue dots at the bottom left. Question is, can we train a neural network using a MLP, or do I need to help the neural network by adding additional layers? I don't know. Let me just go ahead and try my luck with this. Not bad. You can see here, it has nicely separated the orange ones from the blue ones. Again, here, here, one single hidden layer seems to be sufficient. The training loss is getting reduced, as you can see here. Training loss is 0.003 and the test loss is 0.017. At this stage, it has got almost stuck here. I'll stop here. It has run 1,699 iterations to achieve a training loss of 0.002 and test loss of 0.016. Mind you, I'm not change the learning rate or the activation or regularization in this, because they're relatively easier problem to solve. Now, the last one is not so easy. This is the spiral problem. Now, let us see whether we can learn this complicated pattern here. This is the first of the tendrils or the spiral, and you can see a lot of orange dots tracing this path. Then you have the second set of data points. These are the blue data points, and we want a neural network to recognize the orange and separate it out and classify it compared to the one compared to orange. Let me try with a simple MLP. I know that the algorithm will struggle. Let me just go ahead and help the algorithm if need be. Nothing much happening. It is trying, but it is really struggling here. You can see here, 4 neurons are not sufficient. So let me just go ahead and add few more neurons. I have almost added 7 neurons. Nothing much happening here. Nothing much happening here. So it's pretty obvious that a typical shallow network cannot learn a very, very complicated pattern like the one that you see on your screen. So what I'm going to do here is, instead of just having one hidden layer, I'm going to create 2 additional hidden layers. So let me go ahead and create 3 additional hidden layers. So this is the first set of hidden layers, this is the second one, and this is the third one. So there are 8 neurons in my first hidden layer. Let me create at least 7 neurons in the second hidden layer. Here, this guy will have 5 neurons. So usually the first layer has more number of neurons. The successive layers will have lesser number of neurons as compared to the one earlier. So this is a typical deep learning network that we have, because we have more than one hidden layer. Fantastic. Let's go ahead and try this. It is struggling. It is not able to learn anything much here. Not bad. It is trying to come. You can just see here how the neural network is trying to converge to a solution. Fantastic. This is really fascinating, the way the algorithm is working at the back end. There is a bit of spike here, which clearly is an indication that there could be a overfitting problem here. Here again, you can see here the orange line is trying to trace this path, but it is really struggling. Now, this is where I can just help. Wow, this is not bad at all. It's a very, considering the fact that this is a very, very complicated problem, the neural network is still able to learn a lot. When it look at the training loss here, it is 0.004, which is pretty good, and the test loss is 0.024. Now, I'd like to help the neural network. How do I help the neural network? I can now create additional features here. Let's use x1 square, x2 square, the product of x1 and x2. Let's also use sine function and sine of x1 as well as sine of x2. So I've supplied a lot of input variables. The learning rate, if you remember, these are all what we call as hyperparameters. The learning rate, activation, regularization rate, all these are hyperparameters of a typical neural network model. What I like to do is, the existing activation function is tan h. You could use a sigmoid or a linear activation function as well. ReLU is quite popular, so I'm going to try my luck with a ReLU activation function. If you want to, you can also choose regularization. You have 2 different types of regularization, L1 and L2. I'm going to choose the option none here. Let me go ahead and try with a ReLU activation function with the same learning rate, whether I'm able to train a neural network which is able to learn this kind of a complicated spiral pattern. More or less, this looks quite promising. Please look at the path that the neural network has come up with. So this is the orange line, which it has more or less learned. And you can see here, this is the blue line, which the neural network is trying to mimic. Yes, I do agree that there could be a few spikes here and there indicating the problem of overfitting, but this is not bad at all. And we have a lot of neurons here. It becomes a bit difficult to actually fit inside your own head as to what each of these does. I've already explained what each of these neurons do in the first hidden layer. We're going to combine this and sort of link it to the next hidden layer. You see a lot of blobby structure here, which means that perhaps it's trying to learn the patterns in this corner. Similarly, you can see very, very complicated patterns that it is trying to learn in the successive layers. Now, this is a very, very good beginning if you are starting off with your career in deep learning. And I would really, really encourage you to play around with this particular arrangement. You can learn a lot. You can understand the internals. The objective here was to give you a hands-on intuitive feeling of how a neural network works, how we can sort of adjust the weights, how we can manipulate the weights, how we can sort of add more layers or reduce the layers from the existing network so that we can make the neural network learn very, very complicated patterns. Generally speaking, you can add more neurons to a hidden layer or simply add more layers. It depends. They tend to produce the same result. Yes, we can go ahead and experiment with different activation function, but I can just, you can keep doing this the entire day, but I'm going to stop here and request you to subscribe to my channel as well as like and share my videos. So thank you very much for watching this particular video. Have a great day.